This conference will now be recorded.
Good evening. Today we'll be discussing about telescope. So let me first tell you what is telescope and what are the type of telescope available in reality. Yeah, good evening, Deepa. Are you able to hear me? Audible, Deepa? So today we'll be
Sir,
concluding this
audible.
chapter ray optics. Okay, good. So we'll be concluding this chapter ray optics by discussing this telescope. So we'll be discussing astronomical and terrestrial telescopes. Before that, let me tell you what is telescope, what are the uses actually, and what are the types of telescope available in reality. Okay, so telescope is an optical device. So it is an optical device which enables us to see distant objects clearly. Distant objects clearly. Okay, so this is actually here itself we can understand what is the use of telescope. So generally it provides an angular magnification of the distant object. I'll tell you what is angular magnification and how we calculate, quantify the magnification for various telescopes. See, any distant object we will not be able to see in our naked eyes. Okay, even though our range, like the near point and far point of our human eye, like a human eye, is infinity. It is said, but still, in practice or practically, we cannot see more than 2 kilometers. Okay, maybe clearly, distinctly, we cannot see objects. We may see something from very far, like see, we can see mountain from very far, maybe some 100 kilometers away. The mountain is from your like terrace, but you can see the peak of that mountain, but you may not be able to see things over there very distinctly and clearly. So for that, you need to use a telescope. So we'll now see there are different types of telescopes. Broadly, there are two types of telescopes according to their like working principle or the construction. there are two types of telescopes. One is refracting telescope. Okay, one is, so you understood what is telescope. It provides angular magnification. Angular magnification in the sense, suppose you have object over here very far. So generally when you see through naked eyes you may not be able to see distinctly, but when you see with telescope it will be actually magnified angular, like so the telescope will give certain angular magnification such that this object itself will be like come into your view as a big object. Okay, all right. So look, according to the construction there are two types of, okay, so classification of telescopes. According to constructions there are two types. Okay, one is refracting refracting telescope. Okay, so what are these telescopes? Actually they make use of lenses, make use of refraction means you have to make use of lenses. Okay, and here particularly converging lenses, converging lenses. Okay, so make use of converging lenses. Now these refracting telescopes are also two types. What are those? One is astronomical telescope, and another one is terrestrial. Okay, terrestrial. We'll discuss what are these and what are the basic differences between these two types of telescope. Both actually make use of lenses. Okay, converging lenses. Okay, we'll see both this astronomical and this terrestrial telescopes. They both use the converging lenses. Now let us little bit discuss about what is called astronomical telescope, what is called terrestrial telescopes. Okay, so this is one type of, this is actually refracting type. Then another one will be reflecting. Okay, reflecting telescopes, reflecting telescopes. Reflecting telescopes, there are two actually. Newtonian, Sir Isaac Newton had constructed this, discovered this construction, and another one is Cassegrain. Okay, so this is CASSA, SSC, Cassegrain telescope. Okay, there are two reflecting types of telescopes. One is Newtonian, another one is Cassegrain. Okay, so we will mainly discuss these two, and this part you may read from your textbook. There are nothing much in this, so if you have any doubt you can ask me later. And basically why I am discussing this astronomical and terrestrial, because these are the telescopes. In many competitive exam there will be numerical problems from these two telescopes only. Okay, so that's why I'll be actually concentrating these two things. Okay, two telescopes, astronomical and terrestrial telescopes. So now we'll see what is terrestrial, like astronomical, and what is terrestrial telescopes. So let us first discuss what is astronomical telescope. And actually it is used, see, it is the difference in use and little bit of construction difference, okay, between the terrestrial and astronomical telescope. Actually it is used to see or observe objects, like heavenly objects, heavenly objects, okay, like see sky observation centers, then the sun, actually to see objects like sun, stars, okay. Mainly the telescope used for sky observation, okay. So mainly telescopes used for sky observation. So this type of telescopes are called astronomical telescopes, okay. And in this case, we'll see the final object, final image of the object will be, final image created by the telescope will be real and inverted, real and inverted, inverted and what, magnified, and magnified, okay. So here you might be thinking, sir, why uh, then there must be problem if we see anything inverted. No, actually for astronomical objects, like since they are nearly round shape, doesn't matter whether it is inverted or it is like erected, there is no issue with that, because the astronomical objects are nearly round in shape, okay. So these are few things about astronomical telescopes. Now we'll see what is the terrestrial telescopes, then we'll go for to like here actually the main problem or main question will be find out the magnification or derive the magnification of the astronomical telescopes when the telescope is creating an image at the point of or at a distance of distinct vision, that means d. Distance of distinct vision means d, which is nearly 25 centimeter, 25 centimeter for a normal eye. And sometime the image will be created at infinity. So in that case, how to calculate the magnification? So that is the main problem here, which we will be discussing. Before that, let me tell you something about terrestrial telescopes. So look, these terrestrial telescopes are used to see, used to see distant objects on the earth surface itself, earth surface, on the earth surface. Okay, so you might be thinking, like, what are those telescopes? Like, see, we sometime watch football match far from the ground. Okay, see, the playground, like, sometime you will be very like really at the back of the gallery. So if you use a telescope, you can see clearly and distinctly. Okay, and sometimes we use binocular to see very far objects. So those are actually terrestrial objects. That means the telescopes, telescope which is used for viewing the distant objects on the earth surface itself are called actually terrestrial telescopes. Okay, and in this case, since we are seeing earthly objects or the objects on the earth surface, so here final image has to be erected. Final image is erected. Okay, erect image. Okay, erect, and it is actually in this case the image is erect one. Okay, and this is an essential condition for viewing objects on the earth's surface. Actually, correctly, so you need to see an erect image, otherwise it is difficult. Okay, the image is erected, you can say, or erect image. So it is very difficult to get idea if you see an inverted image on the earth's surface. Okay, any object on the earth's surface. So that's why the construction will be a little bit different than the astronomical telescope. Okay, now we'll just go to, okay, these are the few figures you can see. So this is the astronomical telescope. Generally in size, astronomical telescope will be very huge. We'll discuss why it is so. And this is terrestrial telescope. Generally they are smaller in size comparatively. Okay, so astronomical telescopes are very, very huge sometime. Okay, all right. So now we'll just discuss astronomical telescopes and the magnification. Like I said, angular magnification, right? So what is the construction? We'll see first what is the construction, and then see how this astronomical telescope provides the magnification, angular magnification, when the final image is formed at the least distance of distinct vision. Okay, so look, the construction is that it consists of two converging lenses mounted coaxially at the outer end of two sliding tubes. Okay, as you see astronomical telescope, there are two sliding tubes. So at the end of the sliding tubes. Okay, so this you can just sometime increase decrease the length for focusing everything. So this is the tube, you can see that. Okay, so it uses two coaxial, you can see from here ray diagram. So there are two lenses. Okay, two lenses and converging lenses. Okay, one is used as objective. Objective means, it is collecting the rays from the object. And eyepiece means it is actually situated near your eye, through which you see the image. Okay, so the objective, actually look here. Unfortunately in this figure it is not very clear, but still you have to remember that the objective lens actually has a very large focal length and much larger aperture. So, objective, it has number one, larger focal length, and second is large aperture. Okay, large aperture, much larger aperture. So why are these two like this? First of all, there will be a question sometime, why the aperture is so large? It is because, see, the heavenly objects or astronomical objects are far from Earth planet, right? From our Earth surface. So if you want to see that clearly, the image has to be bright. So as much as, like, as much as light comes from the object, it will give you much brighter image. So suppose you collect very small amount of rays from the distant object, the image will not be that bright, and you cannot see, like, it cannot, like, give the better resolution. So for there are two reasons for this large aperture. Okay, one reason is to collect to collect to collect maximum amount of light. Okay, light rays, to collect maximum amount of amount of light. Okay, and second thing is, large aperture, it actually gives you better resolution. Okay, actually these two are related to same thing actually, better resolution and brightness. Okay, so generally if I draw properly, this object has to be drawn like this big, having big aperture, and eyepiece has to be drawn like this. Okay, coaxially, like this. The eyepiece will be smaller, but here in this figure both seem to be the same. Okay, and focal length is also larger. Okay, and generally objective is facing the object. So the aperture is large to gather or collect sufficient amount of light from the distant object. All right, so this is about objective. Now we'll see the eyepiece. So this is eyepiece, okay, which is facing your eye, and objective is facing the object. Okay, so the eyepiece, it is also a convex lens of smaller focal length comparatively. It has comparatively smaller focal length, compared to the object. Compared to the objective. Okay, and aperture also is small here. Why is it so? Aperture is small or smaller compared to the objective. Why is this? Because see, your eye is very small, right? So to to ensure that all the light from the image enters into your eye rather than going here and there. Okay, rather than wasting it, it is ensured here by taking small aperture that the whole light is getting into your eyes to see the image clearly. Okay, that's why aperture is smaller than the objective here. Okay, so the aperture of the eyepiece is taken small so that the whole light of the telescope enters the eye for distinct vision. So this is about the construction. Now what we'll do, see in this case, uh, what happened, see the working principle is that, see the light coming from distant object means the light will be parallel. As you know, for a convex lens, if the lights are parallel to, like parallel lights comes, then what will they do, they will actually converge. If the light is parallel to the principal axis, they will surely converge at the focus. Okay, first focus. But if see there is a certain angle, see these rays are making an angle with the principal axis, but these rays are actually themselves parallel. So rays are themselves parallel, but they are making an angle alpha with the objective lens or the principal axis of the objective lens. So that's why they will meet where, they will meet at the focal length, sorry, focal plane. They will not meet at focus, but they will meet at the focal plane. Okay, focal plane somewhere in the plane. So focal plane means what? So you have the focus. So if you draw a perpendicular plane through the focus, that is called focal plane. So this is called focal plane. So the image will be created as the focal plane by this objective lens. So focal plane is actually the focal plane of the objective itself. So you can see the distant object AB, so it is at infinity as written over here. So the parallel rays which are making angle alpha with the objective at the center of the objective, so they get converged where, at the focal plane. So not at the focus, so they get converged at focal plane, and that's how they create an image A prime B prime. You can see that, you can see that the A prime B prime is the image. So look, objective, I'll just objective produces image at its focal plane. So that is A prime B prime, as you can see from here. So this is the A prime B prime. Now the distance between these two lenses, objective and eyepiece, is so adjusted that the image produced by the objective lies in between focal length and the optical center of the eyepiece. Okay, so if that is the case, we know this, when you have a lens and your object is in between, this is focus, this is center, optical center. If this is in between that, then what will happen, you'll see an enlarged virtual image actually, just beside the object. This is the object on the same side, on the same side, and having the, so virtual object means they will be erect, image will be erect. Look what happens in this case. You see, when the image A prime B prime is inside this focal, see this is the FE is the focus, first focus for the eyepiece. So eyepiece, this is for eyepiece, and FO for objective. And see focal lengths are, respective focal lengths are this, sorry, this is this FE, this is FO. So this is what is the notation. So in this case, look, the object is suppose the image for this A prime B prime is created at the distance of distinct vision of our eye. So that is this one, A prime A double prime and B double prime is the final image, what we will be able to see actually. So this is the final image. So final image is A prime B prime A double prime B double prime, which is actually uh, refracted. See, after it is created after refraction through the eyepiece. Okay, so the position you can see A double prime and B double prime. It is actually created on the same side of the object A prime B prime, and it is actually enlarged and like erect image. Erect means the object and image their height is having the same sign, whether positive or negative. They will be either positive or they will be either negative. So in this case, both are negative. Height, their height is negative according to our sign convention in the ray optics. Okay, so this is the case. Now what is the definition? So I hope you have understood what is the working principle. Working principle is that the objective is kept, and like a large aperture and focal length is also very large. So what happens, the parallel rays which are coming from distant object, they will create an image at the focal plane of the objective itself, and that image, so that image A prime B prime here will act as an image, sorry, act as an object for the eyepiece, and that object is actually in between the focal length. Okay, it's situated in between the focal length. So and highly imaged, like a highly imaged, like highly magnified image will be created A double prime B double prime on the same side, and erect image will be produced. So that is A double prime and B double prime, and the position of the image we are just taking that image produced, image produced, image at the distance of distinct vision. Okay, distance the distance of distinct vision, that is d. So you can see this, the image, final image is created at A double prime B double prime, which is at d distance away from the eyepiece or our eye. Okay, so what is the angular magnification? We have actually discussed already. See, magnification is denoted by small m, and angular magnification is given by beta, angle beta by. So this, as I said, this is angular magnification. Angular magnification we have already defined for microscope. Angular magnification, this is angular magnification. If the linear magnification, if it is linear magnification, then you can write v by u. Okay, for length. But it is angular magnification, it will be actually determined by the ratio of the two angles. What are the two angles? So this is the angle that the image is making at our eye when the image has been formed at the distance of distinct vision, and alpha is the angle made by the rays at the objective. Okay, at the center of the objective. So the rays which are like coming from the objective directly, it is making an angle alpha, you can see that with the objective lens. So this angle is called like yeah, so if you take the ratio of these two angles, the angle may see the angle, see we are, suppose we are seeing through the eye, or maybe with respect to this eyepiece itself, whatever angle this image is making, look, this is the image, this is making an angle. See, this is the image, so this is making an angle beta over here, and this is the rays. So these are the rays, they're making an alpha over here. You can take in the opposite side, so these are opposite angles, so here also it is alpha. Okay, So we have to now see, actually in general beta and alpha are very small, very small. If they are small, then see beta can be written as, or tan beta can be written as beta, nearly equal to beta, or sin beta also can be written as nearly equal to beta, whereas cos beta you have to write as 1, or cos alpha you can write as 1. Okay, so look, this magnification here you can just see beta by alpha. This is the angular magnification as I defined. This is the ratio of the two angles. The angle in the numerator is the angle made by the image at the eyes, okay, when the image is produced at the distance of distinct vision. So this is the condition. So we can write nearly this as tan beta by tan alpha. Okay, now you can use the geometry over here. See, look what is tan beta. So you can just use this look here. So I can use this triangle, this triangle. You can take this optical center E, this triangle. Okay, so you can write tan beta means perpendicular is A prime B prime. Okay, by the base. Okay, base is the B prime E. This is the base, B prime E. This is the base. Okay, now now tan alpha means what? You can just see this is the alpha, this is also alpha. You can take this triangle all the way up to here. This triangle you can take this. Okay, look, I'll write over here. So perpendicular is again A prime B prime by base is actually now O and O B prime, O B prime. Okay, O B prime. Look, I'll just arrange this. If I just arrange this A prime B prime, they will cancel from both numerator and denominator, and see this O B prime will be going there, and this is B prime E will be here in the denominator. Now what you have to do, we have to find out what is OB prime and what is B prime E. Look, I'll just clean this figure nicely. Everything is here, so we will be able to find out what is OB prime. Look, OB prime in terms of the given, see this is O and this is B prime. So this is what? This is actually F0. You look here. Oh, I'm sorry. This is actually, you can take, yes. This is your F0, focal length of, because it is focal plane. At the focal plane it is. So you look here. This is actually up to here. This is F0. F0 means the focal length of the objective. So I can write this as F0, and according to sign convention, it is in the positive x direction. So I take positive. What about BE? What is BE? Look, this is B prime E. This is actually U. Objective. See, the object for the eyepiece, and it is denoted actually in the opposite direction. So I'll take this as minus UE. So what is the magnification you get for this? See, minus F naught by E. Sorry, UE. Okay, this is the focal length of the object divided by the distance of the object from the eyepiece. Okay, but this UE we will not be able to find out, or we cannot calculate this, because it is happening inside the microscope. So I sorry, telescope. I'll just tell you. See what we have got. This m is equal to minus f naught by u into e. So this UE actually happening inside the tube of the telescope. We may not be able to find out this, because this intermediate image intermediate image may not be able to, we may not be able to we may not be able to locate or see. So what we have to do, we have to find out the value of UE in terms of other known terms. What are the other known terms? We know D. Okay, this is the image distance. We know the focal length of each other, like objective and this eyepiece also. I know the focal length. So we'll try to find out this UE in terms of these terms. So look, I know for a length 1 by v is equal to, sorry, 1 by v minus 1 by u. That is the, this is image, this is image distance, this is object distance for a particular lens, object distance, and this is focal length. Okay, this is the formula. 1 by v minus 1 by u is equal to 1 by f. This we know already. Okay, if we use here and look, we have to properly insert these values. V, what is the v here? Final image will be created at this place. So a double prime and b double prime, which is at d distance away. So, and this is actually noted from our eyes or from objective, sorry, eyepiece. So you have to take this as minus d, this v as minus d, minus of this. So u is the, see, in this case u is actually this only, ue. Okay, and ue also you have to take as minus, because according to sign convention. And this is actually, we are writing for this equation for the eyepiece for the eyepiece. Lens's equation for lens is equation for eyepiece, eyepiece. Okay, so now this is minus u, and what is the focal length? This is 1 by fe. So look here, from here we'll be able to get what is ue. So and then we can put it here in the magnification, in the expression of the magnification, angular magnification of the astronomical telescope. Look, this is, so 1 by u is equal to 1 by fe plus 1 by d. Okay, so we'll just put it here in the magnification, in the expression of the magnification, and then we'll get the final magnification. So yes, m is, so this is minus already is there. So this I'll write as 1 by fe plus 1 by d. Oh, actually this should be here, 1 by fe plus 1 by d. Okay, so this should be here, because already 1 by u we have. Okay, so you can see, if you take fe common, then f naught by fe from the down, then it will be 1 plus 1 by fe common we are taking, so fe will go top here by d. Okay, this is the magnification of the astronomical telescope, and this is the expression which you should remember for astronomical telescope when the object is produced at the distance of distinct vision. Okay, and look, in this case, this factor 1 plus fe by d, this will be always greater than 1. Okay, that means it is providing some kind of magnification. Obviously some factor will be added, like multiplied with this f naught by fe. And see, this f naught by fe, these are the focal length of the, this is focal length of the objective, this is focal length of the image. Now see, and this d, we know the distinct distance of, like we know the distance of distinct vision. So these are the terms, so these terms are already known to you, nothing like ue and all. Okay, these are all known to you. If they are asking, they are giving some information and asking to find out the other things, so you can find out using this formula. Okay, now we'll just go to the other astronomical telescope. Like see here, the image is, we'll try to find out the magnification here also. The image is image at infinity. Okay, image at infinity, and that time what will be the magnification? So that is our that is our question over here. So look here, what happens, similar thing, only difference is that here the objective, it is creating an image. So suppose there was, so you can see this image is AB over here. This AB image, you look here, AB image is produced exactly. So eyepiece and the object and eyepiece are adjusted in such a way that the image AB here produced by the objective lens or objective will be situated exactly at the focal length, or for at the exactly at the focus, first principal focus of the eyepiece. Okay, eyepiece. I'll I'll just explain. See the object. This is the image A and B. Where it is situated, it is exactly situated at the focal. See focus of the eyepiece. So this is Fe. This position is Fe. So you can see this distance is here Fe, and this distance is actually Fo. Okay, which is shown here. Okay, the object is, see, for the parallel rays, the object will be the image of the object will be created at the focal plane. Here actually the image is exactly, that focal plane is exactly same as the focal plane of the eyepiece also, or the focal, see this focal length is exactly equal to the image distance of this object. See heavy here. Okay, all right, so I hope you have understood this. Now look, if any ray getting refracted for converging lens or convex lens from focus, then they will actually go parallel to the axis, and then they may not even meet together. So in this case, what happens, this AB is at the focus. So this BA, you can say B or AB act as the image, object for this eyepiece. Here also eyepiece is having smaller aperture, as you can see from here, and so finally the image will be created where? At infinity. Image will be at infinity. See, image will be at the infinity. So in this case, what is the magnification? The same formula, beta by A. Here also we have to see the beta, what is beta and what is alpha. So we can write this nearly tan beta by tan alpha. Okay, what is tan beta? You can see from here. Okay, tan beta means, see, AB by base is actually, I can just take this as, okay, C2. Okay, so B C2, center of this BC2, and in the C, this is the tan alpha. Where is that? So this angle I can take, this triangle I can take, this triangle. Okay, so look here also I will be taking AB by base will be actually BC1. BC1. Okay, now look, AB will cancel each other, and then see BC1 will go up and BC2 will be coming down. Okay, now see what is BC1 and what is BC2. Look, in this case BC1 is actually this one. BC1 is F objective of, see, this focal length of the objective, and this, sorry, for objective, and BC2, you look here, BC2 is the focal length of the eyepiece. Okay, focal length of the eyepiece. So in this case, see the magnification is actually, see the sign of the magnification, you can see this is positive. What does this mean? You will be able to see uh, an erect image over there. Okay, erect image. All right, so you can see the factor 1 plus Fe by D. This is missing at this uh, in infinite. In case of infinite, yes. So in case of that, yeah. So I'm sorry, here also no sign is not positive. Actually, here also the sign should be negative. Let me see here. See the Fe is actually measured in the opposite sign, so it will be negative. So here also it is, because see the image will be real image. Okay, a real image and inverted, but it will be very in, like very uh like enlarged image you will see. Okay, so this is what is the magnification for the case of infinity. Okay, when the object is at, sorry, image is formed at infinity. So in this case actually this factor is missing, you have to see that. Okay, so yeah. Now I'll quickly discuss about the terrestrial telescopes. In this case, as we see, like as we use the terrestrial telescopes for viewing objects on the Earth's surface itself, so we need to see erect image. Otherwise, we cannot get the idea about the images or objects, real objects. So in this case, we use, see, objective lens as well as the eyepiece, like two lenses. Actually here we use three lenses. Instead of two, we use three lenses. One is acting as objective, another one is acting as eyepiece, which is near our eye, and this is objective, which is facing the objects, far objects. And intermediate place there is another lens, what is called, which is called actually erecting lens. Erecting lens means, look, I'll just discuss the principle, working principle, what happens here. you know uh, the objective forms a real inverted image and diminished image. You look here, a prime, b prime. So real inverted and real inverted and diminished image is formed, okay, by this objective, where, at the focal length. Okay, at the focal length here. So focal length of the objective over here at the focus. And look, this erecting lens is such, like adjusted in such a way that the image actually created by objective will be exactly at 2f distance of its own. This is erecting, suppose it is, okay, I'll write only f, 2f distance. So the object is at 2f distance from this erect erecting lens. I'll just repeat it. See, objective is creating the image a prime, b prime at the focus, and this image will act as the object for the erecting lens, and the erecting lens is placed in such a way that, and the lens also will be taken in such a way that its 2f distance, like, will be exactly this one. Okay, that means the image formed by objective will be at the 2f distance of the erecting lens, 2f distance of the erecting lens. So this up to this, it is actually f0. And look, this one actually, this one will be 2f. So the image will be also produced at the 2f distance, 2f 2f distance of this erecting lens. And this will be actually 2f distance, it will be inverted and of the same size and inverted. Okay, and now See, this is actually erect image as the object was like this, but this is now erected. Now this image a double prime, so this image is created by created by erecting lens erecting lens lens sorry erecting lens is placed between or within the focal length of eyepiece, within the focal length of eyepiece. What does this mean? This meaning is that this is the focus of the eyepiece. Suppose this is the eyepiece. Okay, so image may be somewhere here. So you know this, if the object is like this, image will be a prime dot. See, this image is created by the erecting lens, and this will be acting as the object for the eyepiece. And since the object is within the focal length, there will be a virtual and erect image produced on the same side of the object. Okay, on the same side of the object, and final image will be actually erected. So this is how final image will be erected image. Okay, and it will be actually, see, in this case the angular magnification will be same as FO by FE with a positive sign, because the image is erected over here by the erecting lens. Okay, so what are the drawbacks? So here actually you look, the magnification is this less by this factor. This factor is missing. Okay, all right. So the length of the terrestrial telescope is much larger than the astronomical telescope, because you look, you have three lenses. You have this f f objective, then you have 2f of the erecting lens, again 2f of the erecting lens, and then this is again fe. So this length is going to be very large in case of our terrestrial telescopes than the astronomical telescope. Okay, and the length of the, see, in case of normal, so this is called normal, like, see, here in this case the length of the tube, astronomical tube, when this is called normal adjustment, when the image is created at the infinity, that is called normal adjustment of that astronomical telescope. This is normal adjustment. That means image is created at infinity. So in this case the length of the tube will be f objective plus fe. Okay, but in this case look, for normal, see, you will have a telescope having focal length fo plus fe plus 2 to 4f. Okay, this is 4f. So this will be actually larger than the tube length of the telescope. Terrestrial telescopes will be larger than the astronomical telescope. Okay, with this we'll stop it here. Okay, one more point. Actually, the resolution or the intensity of the image in terrestrial telescope will be a little less, because there will be reflection, some reflection by this erecting lens. Okay, so because of that, uh, the image will be, like, intensity of the image will be, final image will be little less. Okay, so that those are the drawbacks. Okay, so I'll stop it here. Deepa, it was like, I thought to finish this like soon, but it took almost 1 hour 5 minutes anyway. No problem. So I hope you have understood this. So is there any doubt or clarification you need? Now go back and read your textbook. You might be able to understand everything what is written in your textbook. Okay, so Deepa, are you able to hear me? Do you understand? You can write in the chat box. Do you follow whatever I have taught today? If you have any doubt, you can ask me now. Okay, I'm not getting any response from your side. You can just write in the chat box. Okay. Okay, you have understood. All right. So I'll stop it here for today. We'll meet again on Wednesday with the new chapter. Okay, so that is wave optics. I think, yeah, we'll start the wave optics. So it was a long, like many classes, like we had to take almost some 12 or 13 classes for this chapter itself, because there are many things to cover in this ray optics. All right, see you again on Wednesday for wave optics class. Okay.